In my previous video, we looked at estimating altitude from a barometer. While it was precise, it had one major flaw, which was the noise in the readings, about 11 centimeters to be precise. On the other hand, we can utilize accelerometers to track vertical displacement, but they are vulnerable to vibrations and are prone to drift. What if there was a way to combine both to get smooth and stable altitude? Well, this is what we are building today, an extended Kalman filter. We will start by looking at the operation model of a Kalman filter, then we are going to derive the equations and implement them on this flight controller, which I showcased in the first video of this series. Ever since I uploaded this video, some of you have expressed interest in purchasing this flight controller. Sad to say, I do not intend on selling it. However, if you still want one, you can get it for just $3 from NextPCB. If you intend on assembling them by hand, then don't be a moron like me. Get yourself a stencil, it is going to make the assembly process a lot easier. Be that as it may, if your intentions are to focus solely on the software, then you can save yourself a lot of time by simply using their PCB as service and get free assembly for up to 10 PCBs. Thank you to NextPCB for sponsoring this video. Check them out from the link in the description below. Now let's look at how the Kalman filter functions. The Kalman filter comprises two parts, the prediction stage and the measurement stage. In the prediction stage, we use the acceleration from the accelerometer to get the vertical velocity and then the travel distance. But we cannot rely blindly on this predicted altitude. This is because the accelerometer is quite sensitive to vibrations as well as contains noise and bias, which when integrated over time produces an ever-increasing error. This is where the measurement comes in. Here we take the measured altitude from the barometer to correct the prediction. But we cannot rely solely on the barometer's reading. As you have seen, it is not very reliable at detecting sub-decimeter changes, and it has an absolute accuracy of just 0.33 hectopascal. So, we need a middle ground between the two. And the way it is done is by taking the difference between the measured altitude and the predicted altitude. The difference is then multiplied by the Kalman gain and added to the predicted altitude to get the new estimate. The Kalman gain determines the amount of correction. But hold on, we are getting ahead of ourselves. Let's slow down and go through it step by step, starting from the prediction stage. Disclaimer, everything you see in this video is based on what I've learned and understood from my research. I am not an expert in control systems. If you find something wrong or want to add more information, the comment section is the place to do so. Anyway, back to the video. First, we need to find the traveled vertical distance or altitude. I'll name it ZK+1 to indicate that it is the new predicted altitude. It is calculated by adding up the current altitude with the new altitude covered. Now, if you go back to middle school, we are taught to calculate distance from acceleration using this formula. Here S is the traveled vertical distance, U is the initial velocity, T is the time interval, and A is the acceleration. We can place it into our equation like so. Zk is the current altitude, Vzk is the initial vertical velocity, dt is the time interval, and Az is the vertical acceleration. But what about vertical velocity? Well, it is calculated using this formula. V is the final velocity, U is the initial velocity, A is the acceleration, and T is the time interval. We can substitute this into our equation like so. Vz k+1 is the new velocity, Vz is the initial velocity, Az is the vertical acceleration, and delta t is the time interval. I'll place the two terms in a 2x1 matrix and name it x. And a fancy name for x is state vector, and it contains our predicted altitude and velocity. Next, we need the state transition matrix labeled as f. The way it is calculated is by taking the partial derivative of the terms of the state vector with respect to z and vz, like shown here. To make it easier, I'll explain the terms like so. Taking the partial derivative of the predicted altitude with respect to z, we obtain 1, and with respect to v, we get delta t. Similarly, the partial derivative of the vertical velocity with respect to z is 0, and with respect to vz is 1. Next, we need to calculate the predicted covariance matrix, Pcap. The formula to calculate it is this. F is the state transition matrix, Ft is the transpose of F, and P is the estimated covariance matrix. The Kalman filter is like, hey, I predict your drone to be here, but I have my doubts, and this is how uncertain I am about it. The predicted covariance matrix shows the uncertainty in the prediction. During the measurement or correction stage, the measured altitude is combined with the predicted altitude to get a new estimate. The Kalman filter is like, this is where I estimate your drone to be, But I have my doubts, and this is how uncertain I'm about it. The estimated covariance matrix signifies the uncertainty in the estimate after we combine the prediction with the measurement from the barometer. There is also this matrix Q. It tells the filter how noisy the accelerometer is, and a fancy name for Q is process noise covariance matrix. For simplicity, I've considered Q to be a diagonal matrix, where sigma z squared and sigma v squared represent the noise of the altitude and vertical velocity calculated from the acceleration. With this, we end the prediction stage. Now let's cover the measurement slash correction stage. This is where the altitude from the barometer comes into the picture. Z is the measured altitude, which I'll assign to z baro for clarity. Next, we need to take the partial derivative of z baro with respect to z and vz, as we did for the state transition matrix. The partial derivative of z baro with respect to z is 1 and with respect to vz is 0. A fancy name for h is observation model. It tells which states can be estimated from the measurement and is also used to calculate the Kalman gain. Before we attempt that, we need to calculate the error by taking the difference between the predicted altitude and the measured altitude. The formula to calculate Kalman gain is this. Pcap is the predicted covariance matrix, ht is the transpose of h, and the inverse of S matrix. S is the measurement prediction covariance matrix and is calculated with this formula. There is a new matrix here, labeled as R, called the measurement noise covariance matrix. It will contain the variance of the noise in the altitude obtained from the barometer. This is about 11 centimeters, but we are going to calculate it later. Since we have determined the value of h, we can pre-compute and simplify this equation to reduce the computation on the microcontroller. Here P00 to P11 are the elements of Pcap. I'll start by multiplying h and Pcap, which yields a 1 cross 2 matrix with the elements P00 and P11. Following that, it is multiplied by the transpose of h, creating a 1 cross 1 matrix with the elements P00. Adding the measurement noise, we get this as the S matrix. Finally, we can calculate the Kalman gain. As we have already determined the value of ht, we can pre-compute the product of Pcap and ht. It might have caught your attention by now. We need to calculate the inverse of S. And since S is a 1 cross 1 matrix, its inverse is simply 1 divided by S, given S is not equal to 0. Now we have the predicted state, the Kalman gain and the error. So with this, we can calculate the corrected state. Finally, using the following formula, we determine the estimated covariance matrix P. I is a 2 cross 2 identity matrix. Just like the previous step, we'll simplify the equations. First, I find the product of Kalman gain and H. Next, the product is subtracted from the identity matrix and then multiplied with Pcap to get this. Similarly, we can simplify the calculation for Pcap, which we had left out, to get this, which marks the end of the mathematical nightmare. If you made it this far, then congratulations, you now know how to create an extended Kalman filter from scratch. Now, we can proceed with creating a C++ implementation to run on this STM32 microcontroller. However, given how poorly my previous video performed, I'll just show you the finished code. The code is sectioned into two files, altitude ekf.hpp and cpp. The former contains the altitude ekf class and the latter contains the definitions for the member functions. The class contains the state vector, predicted and estimated covariances, as well as the process and measurement noise, along with the functions to configure the same, but the meat of the code lies in the run function. It takes two arguments, first the acceleration along the z-axis and the altitude from the barometer. First, the altitude is predicted from the acceleration and then the velocity. Next, we calculate the predicted covariance matrix Pcap using the solution we derived before. Now in the measurement stage, we first calculate the error. Following this, the S matrix is calculated. Since we need to calculate its inverse for the Kalman gain, we need to ensure that it is not equal to 0 by adding a small value in case it is close to 0. Then we calculate the Kalman gain, using which the new corrected state is calculated. At last, we update the estimated covariance matrix P. And this is all that there is to the code. You can find it on my GitHub. Now let's test it out. But first, we must figure out the final puzzle piece. The accelerometer has its own x, y and z axis, called the local or sensor frame, along which it measures the acceleration. But the run function takes the acceleration along the global z-axis, so simply reading the acceleration along the sensor's z-axis and passing it to the run function won't work. Since during flight, the sensor z-axis will not always be pointing up, as the flight controller could be pitching forward, backward, rolling left or right. Hence, the acceleration along the global z-axis will be a function of the sensor's x, y and z-axis rather than just the z-axis. And to obtain it, we need to utilize rotation matrix. The excellent Kalman filter I wrote represents the orientation using quaternions in the global frame, so we need a quaternion-based rotation matrix. Thankfully, Wikipedia has the solution. We can take this matrix and multiply it with the accelerometer readings. However, we are only concerned with the acceleration along the global z-axis. So we can simplify this by multiplying only the last row of the matrix with the sensor readings to get the global z acceleration. And this is implemented in the code like so. Testing it, I can see that no matter how the flight controller is orientated, the global z acceleration reads as 9.81 meters per second square. Next, I kept the board still and logged the acceleration value into a CSV file, and then calculated the variance of the readings, which we will use as our process noise. Similarly, I calculated the variance of the barometer, which is going to be our measurement noise. And with this done, we can finally test our code. This is the test code. I won't be going through each and every line, but instead focus on the core concept. AHRS is an EKF object used for calculating the orientation. Altimeter is the altitude EKF object to calculate the altitude. In the main function, we start by initializing the barometer based on this configuration. Following these, the accelerometer and gyroscope are set to run at a full-scale range of 4G and 1000 dps respectively, with an output data rate of 416 Hz. The accelerometer low-pass and gyroscope high-pass filter are both enabled. This pass sets the HRS EKF object, followed by the altitude EKF object. The sampling frequency is set to 416 Hz, based on the accelerometer output data rate. The process noise is set to the value we calculated earlier, followed by the measurement noise. In the while loop, if the barometer interrupt has triggered, we read the temperature and pressure to calculate the barometric altitude. However, the barometer needs some time to settle, so we need to ignore the first 250 readings, that is for 5 seconds. When 5 seconds have elapsed, we call the update function and pass the barometric altitude to update the predicted altitude. We are not using the run function as both the accelerometer and barometer operate with different output data rate. Next, on an IME interrupt, we read the IME data, calculate the orientation, get the global z acceleration, and then call the predict function to predict the altitude. Following this, we retrieve the altitude and print through the virtual comport. Running it, we can see it is plotting the altitude. Here I lift the board up by 20 centimeters, and the value jumps up by about 20 centimeters, although it is not a stable value. At first glance, it appears that there is not much of an improvement, but plotting the values into a CSV file and calculating the standard deviation, we can observe that the noise is much lower, about 4.6 centimeters. This is an improvement over the 11 centimeters we obtained from the barometer. So does this mean we can finally measure sub-decimeter changes? Well, no, not quite. It struggles with that, as the value fluctuates around by 11 centimeters in the long run. This is to be expected with an accelerometer and barometer combination. If we want better accuracy, we will have to use something more accurate and less noisy like a LiDAR sensor, but I'll leave that for a future video. If you are still here, then thank you so much, and in the next video we are going to look at implementing the Maveling protocol. Also check the description for some useful links.